Hello, welcome back to this course. In the last video, we spoke about the mathematics of computer vision, where we deep dive into probabilities, calculus, and linear algebra. So in this video, we're going to be talking about image processing technique, which is very fundamental to everything you need to know, everything you need to learn when it comes to computer vision. All right, in this video, we're going to be talking about image filtering. We're going to be talking about image enhancement. We are going to be talking about image segmentation. Literally everything that has to do with how you can effectively process an image data. Okay? I want you to stay tuned and listen attentively.
Welcome to class. All right, in this class today we're going to be looking at image processing technique. So, what are the things we are going to be learning from this class? We're going to be learning different types of image processing technique like image filters, image blurring, for instance, the Gaussian blurring, the median blurring. We're also going to look at image thresholding. We're also going to look at image blending, image binarization. What happens when you binarize an image. We're also going to look at image transformation. Then we are going to look at image translation or wrapping. Then we are going to look at perspective transform, quite similar with image translation and wrapping actually. And then we are going to look at image gradient with Sobel and Laplacian transform. All right. Then finally we are going to look at edge detection. That's where our lecture is going to stop today. And a typical edge detection technique is scanning. So we're going to take a little look into that, and then we continue from there in our next lecture. All right, so let's open this notebook and then let's tag along with me. So in the data folder that was provided to you, there's a team mouse order .jpg. I want you to download it, upload it to Google Colab, and then let's process this. Let's do some image processing. All right, are we good to go? All right, so first and foremost, we're going to be looking at image filtering. So in this section, we're going to be demonstrating something what we call image smoothing, image averaging, image blurring, and we're going to be using what we call kernels. So kernels are more or less like filters. Filters are simply is simply an it's simply a matrix, okay, a two-dimensional matrix. So first and foremost, just tag along with me. We are going to be importing necessary libraries. Importing necessary libraries. So we're going to be importing, for instance, we're going to import NumPy. So import NumPy as NP. We're going to also import CV2. That's OpenCV. Let's just say OpenCV as CV. Then we're going to, from matplotlib, import pyplot as plt. And then so let's load our image. So I believe we remember how to load our image. So you just take this, click on this, and then copy the path and paste. All right, so that kind of loads the image. This loads the image as a BGR. All right, so kernel or what we call filter. Let's but before we do that, let's display our image. So we're going to create a kernel or what we call a filter, which is a NumPy array of ones. All right, so we're going to create a NumPy array of ones by this dimension 5 by 5. I would say np.float. We want the numbers to be a floating point. So let's just say we want it to be Okay, just a minute. All right, so this is our image. This is our image loaded as a BGR. So this is the image you're trying to work with. You can see how big it is. It's quite large. So the height is roughly 5K. So if you look at if you insert a new, so let's check the dimension. So it's 9,000 in width, 6,000 in height. So let's create a kernel. Let's call it this, and this is also called a filter. All right, so let's display our kernel. Let's see what our kernel looks like. So our kernel is literally an array of is a matrix or a filter. So the thing now is, let's run our kernel on the image. So let's assume, so to run the filter on the image, you use cv.filter 2d. So cv.filter 2d, that applies the filter to the image, and of course we can display it. But let's do something. I want to display the, instead of displaying the image, let's just, I want to display and juxtapose the original image and the transformed image. So I will use what we call the display function in matplotlib. So let's display and let's juxtapose our output connect function after applying the filter, which is dst, and the actual image, which is img. So display image using matplotlib. So we have plt.subplots. So there's what we call subplots in what they call it in matplotlib. So it helps you to display the image in form of subplots, or display the figure in subplots. So we want our first image to be original, display the original on one side and display the averaging on the other side. So you can read more about subplots and how to display images using subplots. So when we juxtapose, or when we view the image, okay, so now this is the original image. Now after applying the blurring, or what we call the averaging, but let's do it like this. Instead of applying it on the BGR, why don't we just apply it on the RGB? So we need to convert from BGR to RGB. So we can do this. So we can say img is equals to cvt color, where we convert from BGR to RGB. So that does the justice. And then we can also have, so this is RGB, our image in form of an RGB. So we are feeding our RGB image to the filter kernel, and we are going to have the output filter, and then we can run this so that we can both see a BGR and an RGB, and then the averaging form on the RGB. So next, so you can see basically this is the image, yeah, and that's what matplotlib was able to help us do, the subplot. All right, so let's go ahead and do some level of blurring. Let's do blurring. Let's do some more blurring and smoothing. So we have imported our image, which is always the same way with respect to how we import image. Okay, so in this case we want to use a function. We introduced kernel filters. This time around we want to try out what we call the blurring function in OpenCV, but we might not need to implement a BGR or something, but let's see. we might do, should we use the BGR or we should use the RGB? So let's not convert to, let's use the BGR like that, or let's leave it like that. Let's use the RGB. Let's use the RGB. So to blur the image, we have what we call cv.blur. Then you pass in the image, and then you pass in, it creates you pass in the dimension of the filter, which is something like what was initially implemented. What's the dimension of ones and zeros? Ones that you want to pass. All right, and then we can what we call we can then view our image. Since this is a BGR converted to an RGB, so we have the image as an RGB, and then we have the blurring as an RGB. So we can go ahead and implement the same thing that we have here. So you can copy it and paste it under, and then you can say the image and then the blur. So in this case, we want to say blurred. So now what we did was more or less like image averaging, filters. We're just trying to play around with the pixel, and that was the first thing we did. All right, with filters. All right, but right now we're actually looking at this image averaging. It's more or less like you dim. When we say averaging, you are trying to dim your, when you dim your eyes. When you dim your eyes on an image, it's not so bright. But when you open your eyes, it's so clear. The more you reduce your eyes, that's what averaging is looking like. So the more you reduce your eyes, the more blurry it becomes. Do you understand? So that's what we're trying to do here. So when you run this blur, you get this. So you get the blurred form of the image, the original and the blurred form of the image. So let's do some Gaussian. So now, okay, good. Now this doesn't look so pronounced, but if you increase this value to something like, let's say 250, 250, you have something a little more pronounced. So the blurring looks, so you just have to play around with this particular value. And the reason why we are using something this large is because the image actually is quite large. So a small filter of 5x5, or let's say 50x50, is so small that you might not be able to see the effect. But when you increase the size of the filter with respect to, because it's bigger in size, you definitely see the blurriness much more pronounced. So the bigger the size of the image, the more bigger the filter has to be, the filter dimension has to be, in order for you to see the blurriness effect. And the lesser the size of the image, the lesser the size of the filter, so as to see the effect of the blurriness. That doesn't mean you can't use a bigger size of filter on a bigger image. It's just going to be too much. But you just want to see something more pronounced. So you can actually have an image that is blurred and reverse engineer it into its original. That's what we call super resolution. And then you can actually convert an image into its blurry form. So these are basic image processing technique. So another thing I want us to try, we've tried the blur function. We also have what we call the Gaussian blurring. So the Gaussian blurring. So the reason why we are going to load the image again, CV imread, and the reason why we are doing that is because in the previous cell we already overwrote IMG as a particular. We've already overwritten it as RGB. All right, so we've done some manipulation. So we just want to try what we call Gaussian blurring on this. So this is how you implement a Gaussian blur. So in this case, let's try and play around with a Gaussian blur of let's say 250 or 250, or let's say 251. Let's not play with the same value. Let's increase the number by 1. So let's see what happens here. So when we blur out the image, and then so let's run it. So we want to see what a Gaussian blur looks like with respect to the blurring, and then of course plt.subplot, you are able to view the blurred So in this case blur, and so let's wait for this to be done. Now it's going to take, the larger the size of the image, the more time it takes to process. You know, all these things we are still doing, we are not yet using GPU. Some of all these things is still CPU based. So Gaussian blur, so what do we have? So the blurring, you're going to see the blurring a little bit more pronounced. So we've seen the blur, we've seen the Gaussian blur. This is the Gaussian blur more pronounced. Function Gaussian blur. So let's try median blur. So there are different ways by which you can. So blurring is also called smoothing of an image. You know. So let's try out a median blur on an image. All right, and then we already converted to BGR, so blur, and then there are different parameters that you just need to pay attention to. For instance, Gaussian blur, you have to pay attention to this. All right, so let's take this, let's copy and paste the image, and let's see what we get. So let's see what we get. Original, blurred, blah blah blah. So let's see if this value is very small. Let's see if it's going to be pronounced. It's not going to be very pronounced. There will be no much difference actually, but let's see what we get. Then we can increase the value of what our media blurring is going to look like. All right, I hope that makes sense to you. I hope you're getting it. So you can see blurring doesn't look so pronounced like this, but let's say we increase it to, like, let's say 341. I already ran this actually, so I know, you know, different values that you can use. This one's going to even look too extreme, right, with respect to blurring, because let's see what we get. So you can see this is crazy level of blurring. All right, and then you can always reverse engineer this to this, okay, and that's some level of image processing actually. So now let's move into what we call image thresholding. Let's do some image thresholding. So image thresholding is more or less like images of certain pixel that their values are less than a particular threshold. You binarize it, they are zeros, and image with particular level of pixels greater than that particular threshold is a 1. All right, so we're going to be demonstrating what we call image thresholding like we've always done before. Let's load the image, and then let's convert to BGR to RGB, and then of course, but this time around, let's do what we call loading the image as a grayscale. We're trying to threshold actually, but this time around, let's try loading the image as a grayscale. So to load an image as a grayscale, you know, I've always been doing this. So let's do so you pass on the image, and then you put in what we call CV imread as a grayscale. But this time around, we don't want to, you know, convert to BGR. So now we have our image as a grayscale. So one of the things with respect to grayscale is that your image is, the dimension of the image is not going to be a 3-dimension. It's going to be a 2-dimensional representation of the image. All right, so you can see 6000 by 9000. So let's create different thresholding. Let's try out and see. So there's what we call thresh binary. Thresh binary is binary thresholding, which is the one I first of all talked about. There's binary inversion thresholding, there's threshold truncation, there's thresholding to 0, there's thresholding to 0 with inversion. So I'm going to demonstrate all these things. I'm going to write the code right now, and I'm going to display it so that we can actually see the difference with respect to these different types of thresholding. So the reason why we are learning thresholding is that as you advance in your image or in your computer vision career, there are different problems, different use cases whereby you want to apply different types of thresholding. So I'm going to run the code right now, write the code right now with respect to different types of thresholding, and I want you to just look at the difference. All right, so so let's say thresh 1 is CV.threshold. This is thresh binary. All right, so this is binary thresholding, Then we have ret trash 2, which is cv trash old, which is binary inversion, inverse thresholding. So that's how, this is how you implement binary. So we're going to display it and see it. So these are thresholding values. This is the threshold value, 1 to 7. Pixels are always between 0 and 2 to 5, actually. So let's have trash 3. Trash 3. So this is threshold with truncation. And then we can have trash 4. This trash to 0 thresholding. So we're going to see all this visualized, and then we can have trash 5, which is to 0 with inverse thresholding. So let's have different, we want to display them, so let's have different with implots. So let's have different titles. Let's have original image, binary inverse, trunk to 0 inverse, and then let's have different types of thresholding. So we have the image, the actual image itself. Let's say the image has a grayscale, yeah. So this is grayscale, then these are the threshold form of the image. All right, so let's display the image. So let's display the image. So to display the image, we have for high in range, since we have 6 different threshold, 1 2 3 4 5 6. So it's for high in range 6. We have plt.subplot, gray. So subplot is basically 2, 3, I plus 1. So we're basically saying that 2, 3, 0, when I is 0, that is the first image, insert the gray, and then give it this particular title I, and then plot I tick, and then X tick, Y tick, which we don't really need actually, but let's just leave it that way. So gray, then I think there's we can also have this vmin vmax to be 255. So let's see what the plot looks like. So the title is basically you are basically displaying whatever the result of the threshold is. You are trying to display the gray form of it, all right, which is what we have here, and then of course its corresponding title. So when we run this, we have let's see, threshold, what they call it, image thresholding, is actually quite a very, very interesting image processing technique actually. So there are actually different types of thresholding, but this one particularly is image thresholding. We also have adaptive thresholding, and we have Otsu thresholding, which I'm going to take a look at shortly. So while we're waiting for this to pop up, so let me walk you through adaptive thresholding. So with respect to adaptive thresholding, we're also going to work with image grayscale, so we have to cv imread, then our image grayscale form. Well, one thing about adaptive thresholding that makes it different from, all right, so now look at this. We have the original image, then when you do pure binary on the image, all right, you have this. Okay, you binarize the image, which is what we have here, threshold binary. So that is values between 0 and 127, set them to 0. Value between 1 to 7 and above, set them to 1. So that's the reason why you have white and black form of the image. So that's binary. Then binary with inversion basically means that you take this binary form of this image, then you inverse it. Binary with inversion basically means that values between 0 and 127 becomes 1, and values between 127 and 255 becomes white, and that's what happened here. So this is truncation, binary, that's thresholding with truncated level of thresholding. So you could basically see the difference between this and this, quite different. Then we also have thresholding to 0. All right, thresholding to 0. That's more or less like you're trying to threshold the image to its. You are trying to run a threshold on all the values, all the pixel values, to as close as 0. All right, and then to 0 with inversion. That is, you're trying to inverse this. All right, to 0 with inversion. So let's check out the adaptive thresholding. All right, so like we have this loads the image as a grayscale, and then what makes this quite different from the regular level of thresholding? We want to apply some level of blurring. So let's apply some level of blurring to the image, and then let's say adaptive thresholding at work here. So let's just try out the median blur. So we pass in the image, and then what was the value of median blur we used the last time? So you could for median blur we used 341. Okay, so but let's try out the value 5 first. But in this case, we don't want to try out of course. Okay, let's see thresh binary first, then we'll see other type of thresholding. Then T2, that's CV with adaptive thresholding, then thresh binary. So let's just pass in some of these values here. Then we also have adaptive thresholding with Gaussian. So I'm going to walk you through this shortly. So we have this adaptive threshold, adaptive mean threshold. So this is to display the thresholding, and then we have adaptive Gaussian thresholding. I don't want to misspell it. Adaptive Gaussian thresholding. All right, so one thing about this thresholding is that, which is quite different from the first one, is that okay, we're trying to apply a blur, all right, and we're trying to set these different values of thresholding. So we're trying to mix. Adaptive thresholding is more or less like you are trying to take some. So these are some parameters that you might want to go back and check the documentation. So, but in this case, I'm trying to pass the CV adaptive thresh mean C with respect to the binary thresholding, which is the normal thresholding that we just did. Then in this case, we're also passing the Gaussian. So I want you to go and read the documentation, and it's on the slide. You at the last slide, you're going to see some links to the documentation to some of all these things. So in this case, I'm just trying to demonstrate adaptive thresholding. So let's visualize, and I'm going to explain. Let's visualize. So we have 4 different types of thresholding. I'm just using autopilot. Yeah, Colab Autopilot to just write this code. So let's subplot plt.im show the image and the gray form, and then the title. So when we run this, we have the adaptive thresholding, so we can actually talk about it and juxtapose. It's very, very artistic. Actually, it's more or less like you are trying to take out the artistic form of the image itself. All right, yeah. So let's see what we get. Let's see. You know that is because the image is quite big. All right. Another thing is you might want to take blurring, use the actual median blurring, blah blah blah, that we used here. when we use median blur, we actually set it to 341. So we might actually want to try that value. So I want you to try what it's gonna look like when you have 341. All right, so look at, this is the original image, and this is thresholding, which is the usual thresholding that we do, binary thresholding at 127, right, which is this. Then we have adaptive mean thresholding. It looks very artistic. It's like you are trying to use your pencil to draw. All right, so in this case, you're trying to pay extra caution to details. All right, it's quite different from, and in this case, it's thresholding values based, in the first one is thresholding values using the mean, okay, of the pixel, and then in this case it's also thresholding value using the Gaussian, the Gaussian distribution form of the image. I don't want to dive so deep into this, but I want you to check some of these things out and then look at what their documentation says about them. The another thing is, I would love you to try it out when Gaussian went at 341. I used 5 there, so you might want to try out when the value of the median blur is 341, and I hope you're gonna get a very good result. Definitely, yes, you should. All right, so we've done with that, the different types of thresholding, adaptive, and the like. So let's do what we call image blending. So let's take a look at what we call image blending. So in image blending, one of the things I want us to try out is, we are trying to take a particular image, we're trying to take an image and blend it with another image. So let's try and create an image of just a particular color. I don't know, but let me show you how to create. I will have said we should create an image that is all black. So let's create an image that is a plain color. Let's say this kind of my turtleneck kind of color. So let's create blue, yeah, but let's not really create something bluish actually. So there's one library I want to introduce here, that's Peel. From Peel I want to import image, and there's a reason why I'm using Peel. So let's just say from Google, because we want to display it, let's use Google Colabs this time around. CV2 im show. So what's the dimension? So let's get the dimension of the image, tuple np.flip. Go check out what this is. All right, so if you print dimension,
to do that,
you have this. So you're literally just getting the image that we've been working with, and the images we've been working with, and we're just trying to get the dimension of the image, all right, which is the shape. All right, so I'm just trying to introduce you to some more NumPy concepts and the likes, so it doesn't look so strange. So let's create a pure color. Let's call it impure color, and let's call it let's say img.new. We want the RGB, then we want it to have this particular dimension above, and then we want the color, let's assume, let's say 228, let's say 228 150. So now we're basically saying that create an image array, right, where the R components are 228, the G components are all 150, and then the B component are all 150. It's the same thing as saying an array that is np.ones, right? And then you are saying that it should have dimension, which is dimension, right? And you're now saying that it has to have you want all the values to be, let's say, 228, right? Then you now do the same thing for 150. Then you do the same thing for 150. Then you now stack them together as RGB. All right. But that's what this straight line, this is what this line is doing. So it's more or less like the same thing as this. So this is R, this is G, and this is B. And whereas this one is 228, this one is 150, and this one is 150. You know, black is 0, 0, 0. You know, I could have used black, but I'm just trying to use some random, you know, colors that I don't know. All right, so we'll find out what that color code is, right? The RGB of that color. So white is 255, 255, 255, 255. So you could have just, but I don't want to have all black, all white. I just want something in between. So use this random whatever. So let's clear this off just for so let's pure color. So let's convert it to an array in img pure color, and there's a reason why I'm converting into an array, but let's take a look at what img.pure color looks like. What's the type? What does it give us? img.pure color. So this gives us a PAL image kind of property. All right, so that was the reason why I said let's convert it into an array, and this gives us, you look at type img pure color, that gives us an array, ignore by dimension of that particular. So now that I've converted it into an array, let's so we want to display it. All right, so let's resize it. Let's not forget we've learned what we call OpenCV dots resize. So in this case, you pass in img pure color, and let's say it's of dimension 500 by 700, because you know we've been dealing with it on a larger file. So let's do cv2.im show of, let's see what's img.pure color or im array. Let's call it im array. So you know we're using that variable name img. So let's say im array. Cv show, come on, cv show im array. So let's see what our array looks like, or our image actually looks like. So this is the color we get. Oh, fine, fantastic. So we want to blend img. So img, let's not forget img is cv imread this. Then let's convert it to grayscale RGB, the RGB form, img RGB. So we want to blend the, you know, we loaded this as a BGR with RGB. So if you say plt.im show img RGB, so we have this. So let's blend this RGB form of the image with its with that particular color, and let's see what we get. Let's see what we get. So all right, so image blending. So let's do some blending. So let's blend it. So to blend, you use what we call add weight in OpenCV. So here's how to implement it. Image new. Let's call it, so cv.add. We can use what we call cv.add. We can also use cv.add weight, but let's try cv.add first. cv.add, which is np.array img pure color, and then img. So this is add this img pure color and img. Don't forget, if you want to add two arrays, they have to have the same dimension. So if you look at let's say let's do it like this. Let's do it like this. So if you look at img pure color and dot shape, and then img dot shape, you have this, so they are basically of the same size. So that's very, very important. If you want to add two images, they have to have the same size. So next, we've been able to add the two images. So now let's display them. But you know it's going to be quite large, so let's resize them actually first. That's cv.resize img new into 800 by 500, and then let's just play out it show im show im array, and that fetches us this. So that's what it's more or less like, as if you increase the contrast of an image, or you are, if you can do contrast, you might get something similar to this. But what about if we use add weights? There's what we call add weights, and that gives you some level of control actually. So let's say img new cv add weighted. So in this case, we are trying to, like, this is the img, which is no, img pure color. Let's take in the first add weighted. So let's say, and then img. So let's say this one is 0.3. I'll explain that shortly, and 0.7. That is, you are trying to, in this new image, you want to have 30% of this image on 70% of this actual image. So this kind of gives you some level of control actually. So it says this is good. It's good to always have errors actually, so that you can learn. Where arrays have the same size and the same number of channels. Okay, so all right, it has to have the same size and the same number of channels. All right, so I used dot zero. Dot zero basically is more or less like you're taking the first, I think, first row or first column or something. All right, which is not the same size as img. So like I said, they have to have the same size. So you can see the effect of 0.3% of the length, which is this particular color, on this 30% of this on 70% of this. What about if you do 50-50? That's 0.5 on 0.5. What do we have? You have something like this. All right, quite interesting. All right, then when we are talking about binarization, I forgot to walk you through something called Otsu binarization, or Otsu thresholding. So it's spelled like this. I call it Otsu. Otsu's thresholding. It's named after a particular scientist called Otsu. All right, so but let me just quickly show you that level of thresholding in IMRead. You load the image as a Gaussian grayscale. So let's do our normal binary thresholding. So binary thresholding. So this time around, no blurring or something. So ret1 th1. So let's say tv.cv.threshold threshold img 127255 cv thresh binary, and then so let's do Otsu's thresholding after Gaussian filtering. So let's have some Gaussian filtering. So let's do some blur Gaussian filtering. So passing the blur into the threshold, and then so you're trying to have the binary thresholding plus the Otsu thresholding. So let's see what we get from here. Then we also have Otsu thresholding after so let's do Otsu thresholding. So this is after the Gaussian. So let's do one before the Gaussian. So this is before the Gaussian. So let's do this red to threshold, and in this case you pass in img, and then we do also thresholding 3 and 3. So this is before the Gaussian, and so what we're trying to see here is, let's merge some level of threshold binary and auto thresholding, and we want to see what it's going to look like when you binarize an image before you blur it with auto thresholding, and when you apply auto thresholding and binarization after you've blurred the image. So let's say images is img0 th1 img0 th2, then img0 th1 img0 th2, blur 0 th3. So this is blur to th3, this is img to th2, and then img to th1. So let's have their different titles so that we can actually interesting. So when we view this original noisy with thresholding, so I'm going to explain all about these things. Histogram, Otsus thing, and then you have this. Okay, so let's just look through. So I'm going to explain what we get after we run this. So we are trying to run through 3 of them, but there's something we are trying to do. We are trying to look at the original image, the histogram form, and the thresholding. All right, so we're going to do what we call plt.subplot. Let's say 3 by 3, then I times 3 plus 1. All right, so plt.imshow, we are showing when I is 0, images 3. All right, so that is this, and then you're taking the 3. All right, that's the first one. All right, so you're trying to show this. All right, and then let's do the same thing for the next plt.subplot. plt.subplot 3, I plus 3 plus 2, then I plus 3 plus 1. So this is what happens. So we take the first, which is the first image. So when I is 0, it takes in the image 0, so that is 0. Then this one takes in images 0, which is for 3, 3, I, which is 0 times 3 plus 2. Okay, all right, so and that kind of displays the image with its corresponding east, and then the thresholding form of the image, and then the same thing it takes on the next image, the east, and then the thresholding, then the last one, which is the Gaussian form of the image, the east, and its thresholding. So when we run this, let's see what we get. And don't forget, this is the gray form of whatever image you're passing in, and the likes. So while this is running, and while I wait for the result to come up, then I explain. I want to walk you through image transformation and resizing. image transformation and resizing. So now, image transformation and resizing is the same thing as you are trying to resize an image, which I've already actually explained before, whereby you take in a part, you have img, which is cv.imread, where it is autocomplete. All right, you're taking the particular image and then you're trying to resize it to a particular dimension. So in this case, we have then we are trying to resize it, which is the same thing as cv dot resize, which is the image and the dimension that you want to resize. Maybe 700 by, let's say, 500 or something. All right, so let's quickly talk about the Gaussian, this guy. So this is the original image. Original image with noise, which is img, and if you remember, img is simply the grayscale form of the image. All right, and then when you apply the histogram form, when you apply histogram to this particular image, it gives you the frequency of the different information or different data of, pixels are between 0 and 255 actually. All right, so the histogram here kind of gives you pixel value that are more dominant. You can see there's a lot of zeros, values or numbers very close to 0, and there are a lot of numbers very quite close to like the 255 region, and then of course when you apply the thresholding, okay, on the image, so this is what the image looks like. And then when you apply, this is pure thresholding. Then when you now apply Otsu thresholding, you could see the effects of that on the image. All right, so when you apply noisy, now in this second one, right, we are trying to apply what we call the original noisy image, all right, and the Gaussian blur. So in this case, we are passing in the actual image, which is its grayscale form, which is this, and then we are feeding it into an east, which is what is happening in this second line here, alongside the title subplot, and the last one, which is displaying the thresholding form of that image with Otsu. So you can basically see that when you apply some level of blurring on the image, this is what you get, and then this is the original image. So now one of the things I want you to do here to see the difference, or to see more differences, more pronunciation of all these things, is to play around with this particular value of Gaussian blur. We used in the last one that we did up there, we used for Gaussian blur, I think we used 251. All right, so try out, which is going to be another assignment with respect to this. Try out 251 here, and then 251. Let's even run it and see what this comes up with. And you can basically see the effect and the pronunciation when you apply some level of blurring and the Otsu transformation. So basically, image transformation, back to image transformation, while that is trying to run, image transformation with resizing is like you're trying to pass in an image and then you're trying to resize, and this is the image resized. All right, so this kind of gives you a new shape or a new dimension of the image. So if you have an image that is quite big in size, you can always resize it to a particular dimension that literally works for you. All right, I think there's one more thing that I would love to introduce you to before we wrap this up, and that's image translation with wrapping, image transformation with wrapping. So while we're waiting for this one to run, you will get to see the result of this. So this we're waiting for that. So image translation with wrapping. This is the same thing as image. This is the same thing as what we call it's the same thing as what we call perspective transform. And I'm just going to talk briefly about that, then talk about blurring. So you could basically see that the histogram kind of is quite different in this case. You can see this is when you apply the original. This is the original image. This is the normal histogram of the original image and the thresholding. Now this is when you now apply auto thresholding on this particular image. And this is when you now apply the Gaussian filter after you've blurred it. So you could see the difference. You could see this got a little bit darker, you know. So it's more or less like some level of thresholding. This looks much more artistic, right? But I also want you to do some more reading, read through some of the articles, some of the links that were shared, in order for you to understand or comprehend some of all these things much better. And then for image transformation and resizing, you can basically see this image was resized from 6,000, 9,000 by 3 to 500, 700 by 3. So let's quickly look into perspective transformation. So in this case, we want to load in the image. So I'm just going to go straight to the point, and I'm going to explain. So we want to what do you call it, look at the dimension of this particular image, but let's load it as a grayscale. Imread grayscale, so we don't have to worry about the channel. All right, so now we've been able to load it. So this 9,000 by 6 rows, that's 6,000 by 9,000. All right, so let's have, so I'm going to explain this, but I'm going to write something called point one, which is going to be a floating point 32. So I actually mapped these points in the image, and I'm going to explain what I did. So we have, I already jotted them down here, 500 by 6,000, and then we have 500 by 510,000, and then we have 8,000 by 6,000. All right, so these are 3 different points. Then we have PT2, which is NP float. Let's say 32 floating points, 32. So in this case, I want to have 545, and I'm going to explain shortly. So let me just write the code. 3,015, and then 5,000, 6,000. All right, so these are 2 different points. Now what we are trying to actually do is we are trying to take this particular image, which is okay, let me cut this out. So plt.imshow img, we're trying to take this particular image, and we're actually trying to we're trying to take a portion of that particular image, and we're trying to transform it into another dimension or into another form of an image. It's different from cropping. All right, so for instance, and you'll get to see what this generates. You get to see what you generate. So this is this image. We're trying to take it, and we're trying to what do you call it, transform it into another form of perspective or into another form of view. That's what we're trying to do here. But I took some points, right, 500, but let me just show the results so that it becomes much more clear. So for transform, or for perspective transform, we have cv.getAffine, which is pt1, pt2, then wrap affine. I'm going to talk about that shortly. Then so let's just resize dst cv.resize, let's say 700 by 7, and then display. So now look at this, take a look at this. we took this particular image, which is this, and we converted it to we wrapped it and then changed the transform, like change the perspective of the way we view it into another form of transform. So what was done was that I took 500 by 6,000, that is, I took 3 different points, 500 by 6,000, which is 500, 6,000. All right, that's this point, or let's just say 500. 500 is this point here, 500, 6,000, which is this point, right? And then I took 500, 1,000, 500, 1,000, which is this point here. All right, 500, 1,000, and then I took 8,000, 6,000, which is 8,000, 6,000, which is this point here. So these 3 points, 1, right, 8,000, 6,000, 1, 2, 3, but the 3 points I took, then I now transformed it into a new set of points. So I moved this point 500, 6,000 to a new point 500, 4,5. All right, which is what we have here. So we moved it to 500. This is 500, 500, 4,5, and then I resized it. Oh, I already resized it here too. I already resized it to 700, 500. Okay, so if you look at dst.shape, and I had to resize it because dst.shape is quite going to be plt.imshow dst. Okay, so let's do that. So instead of resizing, let's run this. So let's run this so that we can actually see the actual new points. So we took the those three points, right, and then we transformed it into a new point. So it's like you moved the point of an image, those 3 points, then you moved it to a new point, and you drag this to this new point, then drag it to this new point, in order for us to see what we can see right now. That's literally what happened here. So I moved it to a new point 500, 4,5. That's 500, 4,5. Okay, sorry, 500. This is 500, 4,5. This is this point. So we took this point, which is this point here, and then we just wrapped it. We took all this, we took from 500, 6,000. So 500, 6,000, that's this point here. Okay, wait, 500, 6,000, which is here, 500 x 500, then 6,000, which is the y, 6,000, so which is this point. So we took this point and then we wrapped it, we moved it to a new point 500, 400. So this is 500, 4,000, 500, 3,5, right? 500, 4,5. That is 500 in this case. 500, that's x, which is here, and then 4,5. 4,5 is here. All right, yes, 500, 4,5. Oh, sorry, I was looking at it from the x coordinate. So let's not forget this is 0 here, and this is 6,000. So I was looking at that 0, 6,000. So this is 500x, y is 4,5 from 0 here to this. So we took that point and we just moved it to a new position. And the same thing goes for all these other points. We move them to a new position, and that's what led to this transformed view of that particular image. So you can just check it out to have more understanding about what we're trying to talk about here. Then there's one more thing, 2 more things I want to introduce, which is image rotation. image rotation. So image rotation is quite very simple. You do your normal image loading, image loading as a grayscale, and then we can have the dimensions, which is rows and cols, which is im.shape, and then we can have the rotation matrix. So get rotation matrix. Get rotation matrix takes the x comma y coordinate of of the center of rotation, right, and then the angle. So I want to rotate this image by 90 degrees, all right, and the scale. All right, so so when you do plt.imshow dst, it gives us the image, the new rotation of the particular image. So that's one thing that you might also want to take into cognizance of. Then we also have, perspective transform. I think I already explained that. Okay, that's what I just explained. Wrap affine, wrap perspective. So in perspective transform, one of the things you're trying to pay attention to, which is quite different from what has been done here, is that in wrap affine, which is more or less like you're trying to image translation, right? You can just pick 3 different points, but in perspective transform, you are literally picking what we call the 4 points that you want to transform. All right, so you are literally picking the 4 points you want to transform, and you have something like, okay, so now this is the rotation form of the image. So but let's try something, perspective transform, with 4 points. Perspective transform. So for the perspective transform, in this case we have the imread, but in this case let's have it as RGB, or let's say BGR. This is a BGR, yeah. So but let's do the perspective. So the points that I already wrote, that I want to do transform on, I already wrote them down. So let me just float 32, 3800, 1800, 4400, 1800, then 3800, 2900, and then 4400, and then 2900. So those are points 1. We want to transform these 4 different points on the original image into these new points. These new points 0, 0, 300, 300, 300, 0, 0, 300, and so 300 by 300, so into a new point of 300 by 300. So we are taking a point in the image, we're trying to transform it. So then the get perspective transform takes this new set of points into this new set of points. All right, so now let's display it. We have IMG, which is, let's convert to CVT. Let's convert from BGR to RGB. That's the image, and then you wrap the perspective transform, which is the actual image, the transformer, which is the transform here, P transform, and then the desired result, which is the dimension. So when you see this, when you view this, it gives you the image of the boy's face, right? You can even transform it into, you can take different points and just change the perspective view of the image. All right, so that's one thing about perspective transform. All right, for me to wrap up this video, I want to introduce you to something called Laplacian and Sobel. All right, so Laplacian and Sobel, which has to do with image gradients on images. So for Laplacian and Sobel, let's load in the image, cv.imread, imread, which is the actual file content. But in this case, let's just load it as not as a grayscale, as BGR. Then we can convert to RGB. So the Laplacian is taken from the word Laplace transform. Laplace is a mathematical, is a frequency transform from time to frequency. You're trying to take time information into its frequency counterpart. So in OpenCV, we have what we call the Laplacian, and then you apply the Laplacian on the image. So let's see the Laplacian view of an image. And then Sobel is also illustrated like this. So but Sobel is illustrated in two forms, Sobel X and Sobel Y, which is applying Sobel on the x-axis of the image and applying Sobel on the y-axis of the image. So let's display the image. Let's do subplots, and then the Laplacian. Let's view the original image, the Laplacian form, and the Sobel X form and the Sobel Y form of the image. So let's not forget to pay more attention to what this is all about. The subplots 2 to 1. These are matplotlib form of displaying different images. All right. So when we run this, we're kind of literally seeing the Laplacian form, the original image, the Laplacian form of the image, the Sobel X form of the image, and the Sobel Y form of the image. So while that is popping up, there's one last thing I would love to introduce you to, which is going to be where I'll be starting the next video from, right? And that's what we call edge detection. So edge detection is an OpenCV algorithm, and we would be doing a lot of that with the function called Canny. Okay, this thing is still running, called Canny. All right, so to display, I'm going to be walking you through this more about this in the coming video. The next video we're going to be doing. So img cmap cmap. So this is displaying the image and then displaying the edges of the image. So in this case, this is more or less like a thresholding value, and I will talk more about this, but let's just take a peep into what edge detection is all about here. So look at the Sobel and the Laplacian. So this is the original image, and this is the Laplacian transform of the image. So if you want to find the Laplace of an image, that's what it looks like. And it can be used for some high level of image processing. There are some times whereby you could be working with some, for instance, you're working with what they call this thing, X-rays, right? So you might want to analyze the image using Laplace, the Laplacian form of the image. Then Sobel, Sobel X. This is Sobel Y. So this is the Sobel of this particular image from the x-axis, and this is the Sobel of the particular image from the y-axis. I would advise that you take more time to read more about some of all these things, what Sobel X and what Sobel Y is. And of course, edge detection, this is what you get with respect to edge detection. So in the next video, I'm going to be talking more about how we can play around some of these parameters, 100, 200. Okay, so let me run this. Why is it giving me some errors? Okay, CV2. I think my imports CV as CV. So let's see. So that gives us the generation, the edge detection of the particular image. So I'll be walking you through how we can actually detect. Edge detection is basically trying to detect curves or sharp edges in an image. And sometimes we run edge detection because we want to be able to segment an object or extract an object or analyze a particular object within the image, right? So in the next video, I'll be walking you through how we can actually play around this edge detection with respect to segmentation, with respect to image. So this is a particular value that we can actually play around with, Well, I'm going to talk more about, this, how we can play more around with these values in our next video.
Hey, congratulations for making it this far, and I want to appreciate you for listening attentively to me. All right, so in this video, we learned about image processing techniques, right? And I'm very, very certain right now with everything we've learned with respect to image filtering, image enhancements, image analysis, denoising, and so many other things like rescaling and the likes. I'm very, very certain and I'm very proud of you that right now we can analyze any image in the world. Okay. There's going to be an assignment for you. I'm going to be giving you an image to work with, and I want you to follow through that particular notebook that will be shared with you via Google Classroom, right? Follow through every instruction therein, and I'm very, very certain it's going to be very intuitive. It's also very straightforward, okay? Upload your assessment, upload your solution. I look forward to seeing your solution, and I look forward to seeing you in the next class.